All right, yes, thank you. So I'm going to talk today about ESO, don't want to drop the microphone, ESO 323-G77, a type 1 safer AGN, which we've had the luxury of viewing with a few instruments at the VLTI, giving us a nice wide range of wavelengths with which to try and understand the dust in this object. Okay, there we go. So Violetta already gave a really good introduction to AGN, but just a quick recap of what's important here. The unification scheme requires an obscura, dusty obscura, which a few shapes have been proposed. In this talk, we're going to be specifying what's known as the disk plus wind model, where we have an equatorial dust disk, and from this launch to wind. And this, the inner edge of this disk and the launch region, the wind, is what causes the obscuration. And ESO 323 is a type 1, which means that we're looking over the top of the disk and we can see the central region and the hot dust, nice and unobscured. So this is nice in itself, but what's kind of special about ESO 323 is polarization actually suggests that we're looking relatively edge on for a type 1. So we get about as edge on as we can get before we actually start getting obscured by the central dust disk. Now, this is really useful for when you're trying to understand the dust, because if you have this dusty wind that's going across the poles, it's much easier when it's nice and extended, going up and down, as you see in type 2s. But if you want to look at the hot dust, it's easier if it's unobscured, so as you see in type 1s. But this gives us the opportunity where we have both cases as a kind of thing. So the first thing that we originally did was try to, was to use archival data from MIDI on ESO 323, originally as a test between the toroidal model that Violetta mentioned and the disk plus wind model, because in the torus model, the mid-infrared emission is supposed to come from the torus and be nice and equatorial. However, in the disk plus wind model, the cool dust is in the wind, and responsible for most of the mid-infrared emission. And in this case, it would be polar. And indeed, ESO 323 seems to be polar when we fit it with this Gaussian and point source model for the visibility given by MIDI. So this was pretty interesting. It meant that the dusty wind was the preferred model in this case. But what was also quite interesting was that the unresolved source, the bit at the center, was dominant for ESO 323. Now, this was the first polar extended object where the central source was dominant. And this is important because we showed the central source was the Rayleigh-Jeans tail of the hot dust, or likely to be. So this made ESO 323 something good with which to try and test the hot dust. So as such, we observed it with gravity. Now, gravity works on the K-band at 2.2 microns, should be very sensitive to the sublimation region and the hot dust disk. Gravity gives you quite a bit of information, but first we just focused on the visibility, and it's a very simple model, just a single Gaussian. And we find that if we just do this, this Gaussian is indeed equatorial, at least more equatorial than it is polar, especially when compared to the mid-infrared emission from MIDI. So this is nice. We have something in a direction of a disk, but we do a few further checks to see if it is fully consistent. The first thing we do is compare it to the expected size of the dust. So ESO 323 is quite a well-studied object. It has a pretty good reverberation mapping campaign in the K-band, and reverberation mapping gives you the K-band size in physical units. So if we have an estimate for the distance, we can convert that to an angular size and compare it to interferometry. So shown here in red is the visibility at 2.15 microns. And the purple bit overlaid is the model you just saw previously, the single Gaussian. And in orange is the size that comes from reverberation mapping. So you can see it's a pretty decent agreement. So we are looking at kind of the right size. There's a little bit of discrepancy. The reverberation mapping size is slightly smaller, but this is expected because they don't probe exactly the same region. The reverberation mapping is very sensitive to the inner edge, the sublimation region, whereas you get the average brightness distribution from interferometry, which is going to be larger if you don't have an infinitely thin ring. But this is all pretty good, but we've still been ignoring a lot of the data. So gravity has closure phases, which are small for ESO 323, but existent. And so we try to fit a bit more of a complex model. This is the point source model that was briefly in Violetta's talk. where we iteratively add point sources and punish the addition of more sources, and based on this criteria, try to find the best fit. So we find for this data, 3 point sources is really all you need. 2 very bright ones in the center and 1 faint one off the side, which could be asymmetry or some kind of clump. But if we just focus on the central two sources, we find that they are equatorial, agreeing with the Gaussian, which is nice, but also they have a very particular separation. So with the MIDI data, we fit a radiative transfer model to the SED and the MIDI data of the disk plus wind scenario. This was then translated to the K-band, and which is now on the right. So this is just a prediction, not anything to do with the gravity data. And overlaid in the white crosses is the separation of those 2 sources, which you see kind of compares really well to the separation of either edge of the hot dust disk. And just as a final show on the left-hand side and the lines is this K-band prediction just compared directly to the gravity data. So all in all, very good considering this is not fit to the gravity data, it's just a prediction. So in the K-band, we have what we think is a disk. In the M-band, we have what we think is a wind. But we want to now try and see in between. So this is where Matisse comes in. Matisse has L, M, and N, which is 3 to 13 microns, but we're just going to focus on the L and M, which is 3 to 5 microns, and lies between gravity and MIDI. So we tried to do the same thing as we did for gravity with the point source model, except this time using Gaussians because it provided a better fit. And we find that 2 Gaussians is a very good reproduction of the MIDI data. This is incredibly preliminary, by the way, still very much ongoing. So this could change, but what we do find is in the L band at 3.7 microns shown here, we get a decent reproduction of the visibility and a pretty good reproduction of the closure phase, where the red points there are the model, and the purple is the data. And we get this very bright, kind of unresolved source in the center, and then this offset equatorial Gaussian, which is interesting. But it gets more interesting as we go to the M band, where the unresolved source suddenly gets way more elongated in the polar direction. And this equatorial source also becomes a bit thinner and a bit more well-defined. So as for what exactly this means is we aren't entirely sure yet. We think maybe we're starting to probe the launch region of the wind, but that is to be determined. But one final thing, if I have time, is that we did a little bit of image reconstruction. This is very, very preliminary, done by Jacob, whose talk is next. Actually, this was like done last weekend. And on the left, we have the L band, the same one as I showed from the model before, which just looks unresolved. That looks like the beam. Those echoes are probably just like actual echoes, not real. But the M band is very interesting. So the M band, again, you have the beam in the center, but you have this extended stuff to the bottom left. This is very much polar. So if this is real, again, to be confirmed, but if this is real, this is very interesting. So it's above the noise, but it would suggest that the M band is indeed agreeing with the model polar extended, at least a bright component, because this would be the equivalent of this bright component up at the top right. So that's all I'm going to, or I think I have time to go into detail with today. But just to summarize, I have more time than I thought, actually. Fair enough. Well, so we have 4 bands, K, L, M, and N, going all the way across like from near infrared to mid-infrared. We think we see a disk at the start, at the shortest wavelengths, where we see the wind at the longest wavelengths. And in the LM, we are perhaps starting to see the launch region, at least what it seems so far is quite promising. There is still more to do and still more to come. First, we've got to see if we can improve on the modeling. And then we've got to try and include the N band from Matisse to the MIDI data, because the nice thing about the Matisse data is you also get closure phases, whereas in the MIDI, we just really had the visibilities and some differential phases. And we've also applied for ALMA time, which is hopefully successful, in which we can try to get where the molecular gas falls in on this particular object. Hopefully, we expect it to be in line with the hot dust disk and maybe on some in the outflow, depending on whether it survives being ejected. And then finally, we want to include temperature modeling. We've got K, L, M, and N, we should be able to get pretty good temperature modeling. But that is something we have yet to do. Thank you very much.
Okay, thank you very much. Questions in the audience?
I'm Leighton from Concordia Observatory. Thank you for the nice talk. So I want to ask your gravity modeling, including closure phase. So if I understand correctly, the final model is one elongated Gaussian and a 3-point source.
That Gaussian in the bottom is the beam size. Sorry, that's not that's a rough estimation of the beam size. It's just 3-point sources.
Just the 3-point source.
Yeah. Any more was we used the Bayesian information criteria to punish the addition of more parameters. And if we did 4, we didn't get a good enough improvement to warrant an extra source, basically.
So, but you get same level of fitting with the model with limited size, right?
Right.
So here is you use point sources, but in your previous model your source have a size.
Yes.
And both can fit.
Yes, so they're fairly consistent between the Gaussian and the point source in terms of size. It's just one, this is a bit of easier to compare to like either edge of a ring, but a bit more consistent. And also we wanted to see if the closure phase would introduce too much extra detail. As I said, that faint source off the side is necessary to do the closure phase. What this exactly represents, we'd need to do much more study into it, because this could be a distinct clump, or it could be just asymmetry in the direction of the disk. It doesn't necessarily, just because it's the limits of using point sources to try and explain what is probably a continuous subject. So that would require perhaps more gravity observations to be able to make that distinction. Something to be done perhaps with Gravity Plus, because we could only use low resolution fringe tracker data.
Thank you.
Okay, so let's thanks again.